So what can we do for firming? We've seen that spreading resources around geographically helps, overbuilding helps, but really we want to something else. There are problems with all of those, and the solution is generally thought to be energy storage. That when we've got the sun shining and the wind blowing, we store up some energy and then we play it back at later times when we need it. So let's talk about the different forms of energy storage and their relative merits. These are slides I've borrowed from Lachlan Blackhall, who gave a guest talk at this course. We've seen this graph before, the demand side analysis. This is day of the year, hour of the day, how much electricity is demanded in Canberra. So we've got the summer peak in the late afternoon and the evening and morning peak in winter when you're heating places up. And here's the amount of power you actually generate from the sun. And one form of storage is just for a few hours. Generally speaking, in most parts of the world, solar energy is at its most in the middle of the day, whereas the demand is the most a few hours later. So a short-term shift, enough storage to store up that solar energy during the day and shift it over to the evening afterwards. And that's a relatively straightforward problem because you don't have to store too much energy, just enough to move it from day to night, storing for a few hours, just a few hours usage. On the other hand, there could be more serious and rare situations, like if you have a week in winter with no wind and no sun, or something like that. And that's a somewhat different problem. You can look at all these things in terms of how much energy you need to store, and the power rating, how rapidly you can put it out, and look at different response times. If you're storing a lot of energy at a low power rating, then it can last a long time. There are different technologies. On the diagram on the left are different sorts of chemical storage, different sorts of batteries, lithium-ion batteries, sodium, sulfur, lead acid, zinc bromide, and also supercapacitors, which are only good for very short periods of time, but are very good for those. And then there are kinetic storage, which is where you store energy either in potential energy or kinetic energy, like a flywheel. CAES is compressed air energy storage, and this is pumped hydro. And we'll talk about these all later. So these, you're going to need some short-term storage just to move the daytime peak of the solar into the night and deal with short interruptions in the wind, and some longer-term storage, which is designed mostly for when you get these long periods without much power. Now, what are you looking for in storage? You need a power rating, which is how rapidly it can absorb or dump the power, and a storage capacity. People often get these two confused. So let's say you're putting out 100 kilowatts. How long can you do it for? If you've got 100 kilowatt hour storage, you can put out 100 kilowatts for an hour. Some systems, like batteries, can put out enormous amounts of power, but not for very long. So this is always important to think about. There's depth of discharge. How low can the power go, the storage go? Round trip efficiency. So if you put power in, what fraction of it do you get out? Or is some of it wasted in going in and out of your storage system? There's a number of full cycles over life. As we know, mobile phone batteries only last a few years, and most batteries, there's only a limited number of times you can recharge them before you need to replace them. And if you're going to build billions of these things, that could be a huge industry, just constantly replacing and recycling batteries. Response time. Let's imagine something goes wrong and a wind turbine cuts out. How quickly can you supply the power? Ramp rate, how rapidly you can ramp up. If you've got it stored, does it just stay stored or does it slowly bleed away? So can you store it for a week, a month, a year? And also, how big are these things? Is it going to occupy hundreds of square kilometers, or can you fit the power in a small region? So these are all important considerations. Another factor that's really important is we live in AC electrical circuits, alternating current, that has a particular phase of electricity coming in and out. And if you have an inverter on a wall and it's putting out electricity but it's not lining up in the phase, it can actually partially cancel out the energy being supplied by generators. All these different generators have to be supplying electricity in phase. Now, that wasn't a problem when there were only a few giant power plants, and each power plant was a huge, great spinning piece of metal. That meant they kept time very naturally. But when you start having millions of software-controlled inverters around the world, they have to all keep in sync, and that can be quite tricky. Um, how do they even know what the time is? How do they synchronize between themselves? This is, I think, seen as a solved problem now. By having some utility scale batteries, they can maintain this synchronization, but it is an issue.